All right, so during the class, we derived this Gaussian equation for the conduction in one-dimensional. On the right side, I have one-dimensional here. And then, however, if it is a three-dimensional thing, then you would not only have the x component, but also you would have a y component and a z component. The derivation of this will be exactly the same as what we talked about in the class, using a unit volume, and then you construct the first law of thermodynamics for that. And then now not only have the x component, but also the y and the z component. Overall, it is still equal to the change of the internal energy on the right side of the equation. So therefore, it is density, specific heat, and then the temperature change with respect to time. This is a three-dimensional case. And we write in this format. And I also box it as compared with the first box on the same page, the first line of this slide. And one thing here we can rewrite is we can move the density and the specific heat to the right side. And then if we define this as a combined parameter, it's called thermal diffusivity. And for thermal diffusivity, some parameter, some property table actually has this thermal diffusivity. I recorded a video a couple of days ago to show you how to look for properties of the substance of a material. And then some table has this thermal diffusivity. And then if we use this combined parameter, then this equation in the black box can be rewritten as the thermal diffusivity times the second derivative of the temperature equals to the temperature change with respect to time. And then this is actually similar to the mass transport scenario. If this is for mass transfer, then we would have the diffusivity times the concentration secondary derivative, the gradient, equals to the change of the concentration with respect to time. And this is actually why we call alpha as the thermal diffusivity, because it is equivalent to the diffusion coefficient D in the mass transfer case. And then if it's one-dimensional, then this equation using the alpha will be alpha second derivative with respect to x, that would equal to temperature change with respect to time. And if it's a steady state, this is also a special case of this equation. The steady state means anything that we are talking about, whatever parameter it is at a steady state, that parameter doesn't change a long time. Steady state means a change with respect to time equal to 0. And this makes the equation simplified as this. So I'm going to box this guy as well, which is a steady state conduction equation here. All right, so these are the general equations in the three black boxes. And then sometimes you can even box this guy as the same equation as the second black box. All right, the steady state box is at the end of the slide here. Okay, And now let's look at a few special cases. If we have a bar and the length of it is L, the length of the bar is L. And then because the cross section is so small and it is a bar, so we ignore the other directions. We only consider the Y direction. And again, this is Z and this is X, and then this is Y. So this is the Y direction. So this is one dimensional at Y. So if this is at steady state, then the equation to describe the temperature along this bar is this equation. The second derivative of temperature with respect to Y equal to 0. Because at a steady state, that's why it's 0. And then if you have this equation, and then we look at the boundary conditions, hopefully in future I can use BC, boundary condition at Y1, we have temperature 1, at Y2, at temperature 2, then we integrate that equation, the second derivative equation, once we get dy dt dy equals to a constant C1. And we integrate again, what we get is T equals to that constant times Y plus another constant, right? Or you can do the integral with the boundaries, or I do the integral without the boundaries here. And then we can plug these two boundary conditions into this final solution to solve for C1 and C2. And what we get is T equals to T1 plus, this is C1 and then C2 all solved together. And then if you want to plot it, this is Y, this is T, and then what you have is something like that. This is Y2, this is Y1, this is T1, and this is T2. And by the way, these two boundary conditions, T1, Y1, T2, Y2, doesn't have to be at the ends. It can be anywhere along any two positions along the Y direction. And then this will be the solution, general solution. And then of course, if you have the values, the numbers, so if say T equals to 20C at Y1 equal to 0, T equals to 80C at Y equals to, let's say, L, then what you get is T actually equals to 20, that's T1, plus 60, that's T2 minus T1, and then that is L, and then Y minus 0 if you want, that's the actual Y, because Y1 equal to 0. All right, so this is a one-dimensional special case at a steady state for this generalized solution boxed in the black box here. And then the second type of special case we talk about is actually a two-dimensional case. Let's say we have a thin sheet. So if this is a very thin sheet, and then because it's thin, so the x direction can be ignored. We only have y direction and a z direction. And if we have two boundary conditions, let's say T1 and T2 here, the thickness is x, delta x equal to 0. So let's say L go to 0. The L means thickness. Zero. And then what we have is actually, we have, don't forget, our equation is still this. If it's at a steady state, let's say at steady state, thin sheet at steady state, what we have is this. And then because the x thickness equal to 0, so that becomes 2d problem. And what we have is actually second derivative with respect to y plus the second derivative with respect to z equal to 0. So the t will be a function of, I just say t would be a function of y and z location positions. And then, of course, if you have T1, T2 as a boundary condition, then you would be able to solve it. And then this actually will be a problem that we're gonna solve towards 1/3 of this semester. All right, so I use this video to go through these special case of equations from what we got in the class, one-dimensional and a three-dimensional, and then steady state. These are the one-dimensional steady state and two-dimensional steady state equations. All right. So in the class, we will talk about some other coordinates. So far, everything is at x, y, z coordinates. So far, all in x, y, z coordinate system. Okay.